Okay, so the last topic was discontinuity and continuity, examples of continuity and discontinuity, how what difference it makes. But at the end, this was the very last topic, especially compositions and how substitution rule works for continuous functions and cannot work for continuous ones. So we did it a few times. Asymptotes was the last topic. So describing graphs with using the language of asymptotes that you can see on the right. So that is the indicating how you might be starting with this, and then you're providing the answer. That is just happens often enough to pay attention to. A picture, and you're supposed to describe it, so you don't even have to provide any explanation. Okay, so that's roughly what you see here. The answer using the language of asymptotes, but then the more precise language is the language of limits, and you still can do it in 3 different ways. Okay, so the thing that, however, is maybe of a challenge. I don't think this is really, but remembering examples of functions with or without asymptotes. So that's once again in the spirit of providing examples for every concept, as many as possible. Okay, so you need to know those. Another something else that might be challenging is actually finding, if you remember, how do you find what is the opposite kind of problem? What if you have a formula? Then how do you find asymptotes? So say f of x is equal to x squared minus 7x cubed minus 1, and you ask to find asymptotes. So remember how? Set a denominator equal to 0 in order to find what? To find vertical asymptote. So x cubed is equal to 1, which means that, so careful with algebra, we're not really studying algebra, so I'm assuming that you know how to do it. So x equal 1 is the only asymptote, vertical asymptote. Okay, so x equal to 1, it is literally an equation with straight lines, straight vertical line, x equal 1. Okay, so x equal 1, which is on one hand, it is a solution. That's how you would write the solution to this equation, x cubed equal 1. But on the other hand, the answer gives you right away the equation of that line. Same with y's. Okay, that's next. But now what I was trying to say here is you still, there's a little extra step here is once you find set denominator equal to 0 and solve it, x equal 1, you have to make sure that the numerator is not equal to 0 at that point. Otherwise, you have an indeterminate expression. So then you have to verify x squared minus 7 is not equal to 0 at x equal 1. Okay, so that confirms that it is a vertical asymptote. Okay, so then you just say, once you have that, you just say part of the answer, x equal 1 is a vertical asymptote. Okay? Technically, and we already know how to express it, well, although we didn't do it, so let's do it one more time. So a second way to say it, without words, but with limits, you say as, well, in the language of limits, the one that above, versus the language of asymptotes, words, is more precise, not only in some kind of a mathematical sense, but in some general sense, but mathematical language versus English language, there is more precision there, but also it provides you with some extra information. For horizontal asymptote, it was whether or not you have an asymptote on the left or on the right. So just saying that x equal 3 over there, horizontal asymptote, is ambiguous because you might have it on the left, on the right, on the left, and on the right. Okay, so the 3 possibilities are hidden in that phrase. See one over there. Y equals is 3 is a horizontal asymptote. There are 3 possibilities, and they are all fall onto this category, even though the picture gives you only 1 out of 3. Okay, so in a similar situation here is vertical asymptotes. The difference, just the way I said it, let's ignore the possibility of let's ignore the function itself, and suppose all you know is that x equal 1 is a vertical asymptote. So this is the line. How many possibilities behind this phrase? Really distinct possibilities. So in other words, in what way can a function approach its vertical asymptote?
Is it
4,
four?
right. So can you describe them?
Each one of them will be towards the
Yeah.
going up the top.
Yeah.
Two of them will be going up top. Two of them will be going up the bottom.
Yeah, and then you can flip it. That's right. So like this. 4 possibilities indeed, and each of them are described by different limit situations, and those limit situations are described with different kinds of one-sided limits. So I don't want to split them. As you can see, first of all, observe how different the functions are. So we concentrate on pretty much the vicinity of one particular number, 1, in all of these cases, but the graphs look very different. Okay, so let me describe these with limits. In fact, there are only 2 situations, left and right, for us to worry about. So how do I describe this situation? X goes to 1 minus y goes to plus infinity. Okay? That's how this situation is to the left, what's happening to the left of 1. Okay? So the opposite, so once again, 1 with a -1, that's a superscript. In the one with negative sign, in the superscript gives you x approaching 1 from the left. Okay, so and then for the other one, it is what x approaching. Well, I'm sorry, I have to be specific here, as x approaches 1 plus y approaching also plus infinity. Okay, so that's another way to describe this little behavior. And then you can see how you just vary those pluses and minuses. I mean, there is a 1 and there is infinity, and you can attach to 1 plus or minus, you can attach to infinity plus or minus. That's what makes 4 possibilities. Okay, so so that's roughly how it works out. But and then you realize that then this language is incomplete. So the way I describe it here is then is incomplete. We got to pick which one of the 3 or for the 4 is correct. So how do we do it?
You can plug in values.
Yeah, you could if you pick values close enough to 1, then there should be no ambiguity. Identical to that idea is pretty much using a graphic calculator. Okay, so it's the same thing, plug it in, except you have to. It's calculated does it for you. Okay, so if you want to do it algebraically, so there would be no doubts of what's going on. So you can say x is like 1 minus epsilon. So 1 minus, it's epsilon is a small number. So suppose x is just slightly less than a 1. Okay, then what you look at is numerator and denominator and see their signs. So the numerator is x squared minus 7, and what kind of number is it? Positive or negative? Negative, right? Because it's just less than 1. And then the other one is x cubed minus 1. Positive or negative? It is indeed negative. Yeah. Okay, so then altogether the whole thing is positive, which means that it is plus infinity. So this is actually the reality of the situation. Okay.
What is it? What happened?
We looked at the sign of the numerator separately and the sign of the denominator when x is close but to the left of 1. Okay, so that's the way to write it. I don't want to write. We never say x equal 1 minus because it's not a number, but x minus epsilon, where epsilon could be any small number. As long as the epsilon is positive, that's what we're talking about. And then you will do the same with 1 plus epsilon, and then once again. So you can see what has changed. The only thing that's going to change is not the numerator. numerator will be still negative, but the denominator becomes positive if we take x larger than 1. And then so it will be, the picture then will be, which is the correct picture? Which one? The third, right. This one. Okay. Okay, so that's vertical asymptotes. How do we do horizontal asymptotes?
The leading coefficients.
Leading coefficients, yes, but I don't want you to remember the answer is still a limit. So it is a little bit easier. That's how you compute the limit. You look at the leading coefficients, but you have to set up the limit. The horizontal asymptotes are not only you compute the limit and then say what the asymptote is. It is a limit. Okay, so as you can see, this is the limit we're talking about. So you can actually take your function, it is given explicitly, and create a limit and compute it. And then how do you compute it? You look at the leading coefficients. Okay, so in this particular case, how do you find it? Compute limit. What is our function? X squared minus 7, x cubed minus 1, and with x going to infinity. Frequently, you don't care about which one. It works out both ways. And then how do you compute it? Look at the leading coefficients, or more precisely, leading terms. So the two leading terms, x squared, x cubed, the rest is gone. So the leading coefficient combined together give me what? The answer is 0, but if you cancel them, you have 1 over x, and x goes to infinity. The answer is indeed 0. So x equals 0. Y equals 0 is the answer. There can be, remember, there can be only one horizontal asymptote. Okay. Okay, so the limits all satisfied with all the algebraic properties of limits are applied to these limits as well. By the way, since we are looking at the whole thing altogether, a method for computing limits like that. What's the other method that came up later? The leading terms is probably the best way to do it, but just to mention it, what's the another method from recently? Computing limits of fractions with indeterminate expressions. This is an indeterminate expression, right? X goes to infinity. Both numerator and denominator go to infinity, which creates an indeterminate expression, and that's why we need to do something about it. Otherwise, we just would have applied the quotient rule. We don't, but we solved the problem. But worth mentioning. Yeah. Yeah, well, it is in essence it's the same method. Leading just it's you pretty much rather than having like a rule of thumb, you explain how that rule of thumb appears. Okay, what I'm talking about. Well, remember what this stands for? L'Hopital's rule. Okay, so that is very recent and it involves derivative, right? So that's another way to do it. And so what you do you differentiate numerator and denominator. Okay, and then see what happens. As long as it's an indeterminate expression, that is a pretty powerful method. Okay. Okay, so polynomials. Okay, so all functions are continuous almost all the time. Okay, what else do I have to? I think I never showed you this. This is what I'm reviewing. I guess I'll just I don't have a picture, so I'll just go to the page, and there is which is what I'm looking at anyway. So it's about limit flowchart for limit computation. I don't think I showed it. Okay, so it's kind of right here. Let's do Okay, a little bit smallish, but it'll do. It's a big file. Okay, so a flow chart. Okay. Okay, 100%. Yeah. Okay. I try to make it like an algorithm for following, like almost like a I don't know, income tax report or income tax filing. So go through steps. So can you read it? So computing the limit if where f is a function typically. If it is continuous, then just substitute and you're done. Okay, that's the if you proceed to the left. Okay, if it is not a continuous function in the first place, so such as fractions that we just saw, then you have to break it into algebraic operations. Okay, so sometimes it's simple, or it's not. It's not. No, probably no isn't really not the correct answer. It is possibly you don't know. No means maybe. Yes, it means yes, and no means maybe. So then you discovering. Then as you move along, you will discover whether or not it's continuous or not. Okay, so if it's not, then you break it in algebraic operations, hoping that each parts of those parts of the function will be continuous. Okay, so the four operations are just subtraction, multiplication, and division, and you break it apart and look at those expressions separately and see if the result is indeterminate. Indeterminate expressions are plentiful. Infinity over infinity, just 1, 0 over 0, infinity minus infinity. Okay, so all kinds of nasty things might happen. Infinity minus 5, is it indeterminate or not?
It's 5 less than infinity.
Yeah, what is it? Does it make it's still infinity. So infinity minus 5 is not indeterminate. It's infinity. Infinity plus or minus any number will give you any number. So infinity multiplied by 5, what is it? Is it determinate or indeterminate?
It can't be determined.
It's determinate, sure. No, it's still infinite. Multiplied by 5 will remain. But if you what?
Still infinity.
It's still infinity. You might flip infinity if you multiply by a negative number. Positive infinity becomes negative and vice versa. But it's still infinity. But if you multiply by 0, then what? Infinity times 0, what is it?
0.
No. It's indeterminate. We did not look at all indeterminate expressions, but the logic is always the same. Why are they indeterminate? Because when we encounter something that we're not sure, when there is either operations with infinity or you have division by 0 or anything like that, the indeterminate, why it is indeterminate? Because if you go back and think of each of those numbers as a limit, then the result might be multiple. And so that's, remember, infinity over infinity might produce infinity, might produce 0, might produce a number, might produce total divergence. Okay, so same with 0 times infinity. It's not 0 nor infinity necessarily. It could be. So as an example, here's 1 over x times x. X goes to infinity. So if you just try to apply the product rule, you'll have what? 0 times infinity. But what is the reality?
It goes on forever.
What?
It goes on forever.
No, what's the limit? What's the value of the limit on the left? Not on the right. On the right, you have an indeterminate expression. What's the?
I feel like it's 1.
Why do you think it's 1? 1 over x multiplied by x. Why do you think it is 1?
Because if you...
Of course it is 1.
5 times 5? Or 1/5 times 5.
right? So it doesn't matter what x is as long as it's not 0. It's 1. So there you go. So the function is equal to 1. The limit is equal to 1. Okay. So what if I put 2 over here? What difference does that make? On the right, it doesn't make any difference on the right. It's still 0 times infinity. Well, on the left, what happens?
It becomes 2.
It becomes 2. So the answer suddenly becomes 2, even though as an expression, if you try to apply the product rule here incorrectly, then it produces 0 times infinity, and it is not infinity. So we quickly got 2 answers for the same indeterminate expression. That's what makes it indeterminate. You look at 0 times infinity, you remember this little formula there. It could be 1, it could be 2. Or it could be infinity, or it could be 0. That's the thing about indeterminate expressions. It could simply diverge. It's another possibility. So just cancel each other, and that's it. Okay, so there are plenty, just too many indeterminate expressions to study them separately. So just watch out. And whenever you see an expression that you are not sure about, then you probably got to go back over here and re-examine the whole thing, which is what this is, what follows. Is the resulting expression indeterminate? So by default, if you're not sure, assume that it is. Okay, if it is not, then but if you for sure that you know that there is not indeterminate expressions, then the answer is no. And then you go back and do the same thing with each of these expressions. So that's the route on the right. Go back and follow the same procedure for each of the terms that you've got. Okay. However, if you suspect that that's not the case, that one of the expressions that might be indeterminate, then you got to go back and deal with each of the expression algebraically, which is what we just did a minute ago, right? That's what we did. We saw an indeterminate expression on the right. Okay, we identified, or at least we were doubtful, is it determinate or indeterminate? Okay, so if you're in doubt, go back, do algebra with your expression, which we did. We discovered that there is nothing complicated about the function itself. It is in fact 2, and then we compute the limit and we're done. Okay, so that's what this diagram is supposed to suggest. And then you might have to repeat it many times if it is very complex. Certainly don't expect you shouldn't expect anything especially complicated on the final. So understanding the concepts is what hopefully we'll achieve. Okay, so all right, so we're getting finally to the derivative. So separately, two separate issues actually is derivative on one hand and differentiation on the other. So one is the conceptual understanding of what the derivative is. The other one, the techniques of following those derivatives, following how to get from point A to point B with those through those rules of differentiation that we have seen. So, but first is the derivative. So that was a little bit of a controversy on the last test. What does it mean to compute the derivative from the definition? And the answer is from the definition is a limit. Okay, so whether or not you are computing from the limit doesn't really matter, but you do have to know what that limit is. Why? Because computing the derivative is really not the center of everything. Not really the problem of calculus. Very frequently, you are walking in the opposite direction. You manipulate some formulas, and then you see an expression that you're supposed to recognize as somebody's derivative. When you see the expression, you should know that it is the derivative. Then you move, rather than from left to right, you move from right. Instead of left to right, you go from right to left, and then you know, oh, well, it turns out this is the derivative. In any kind of applications, if you try to develop a theory, well, maybe in your project, I'm not sure if you encounter that, when you are thinking about what's going on in some practical problem, and then you realize that what you're thinking about actually has a concept in calculus for you to use. Either it is a derivative, or it could be an integral. Either way. So anybody, I can't remember what you may have encountered. Remembers the example of facing this?
I had to find the derivative.
Well, no, exactly. The point is the opposite is when you didn't have to find it, but you had to recognize that the problem that you're solving is in fact about the derivative. Because the problem, as it's stated, none of you have the word derivative or integral in it. So you had to make that connection yourself, right?
Anybody have to find an integral?
Yeah, okay, so let me try to remember what those problems were. Well, in your case, well, for example, the slope is the derivative to begin with. Okay, secondly, if you do optimization, you do have to set derivative equal to 0. So that part is more typical as what we have encountered. The idea of the project was to give you experience with recognizing mathematics, when nobody tells you it is mathematics. Right? I mean, you know it's mathematics, but what exactly is it? What other problems were? So with the Archimedes construction, okay, so tangents, right? So if you have a curved mirror, then to know where exactly the light will bounce off in what direction, you need the tangent line, and tangent line is the derivative of the function that represents that curve. Okay, so did Archimedes make that discovery then or something like that? Maybe not. They didn't really think a lot about functions at that time, and so that's the only problem. Okay, and I don't remember what the rest of the problems are. Well, anyway, so this is, after a while, this is a more important direction. Okay, so, and then of course, but in any doubt, this is a very abstract way to put it. So even though you should remember that formula among the number one formulas that you put, in your head, there is always a metaphor or a concept that allows you to test your understanding, and that is motion. Remember, a lot of just about every concept in mathematics in calculus 1 can be represented in terms of motion, as just the way Newton did. So then what I'm talking about is so y equal f of x time, y location. Okay, and then f prime. So then we have a relation of location as it depends on time. F prime then is what? F prime? Velocity. So then depends on your background. Do you really feel comfortable that understanding velocity, you bring to the calculus class your own understanding of the velocity, then it helps you to understand derivatives. It could be the opposite. Maybe you learn something about the derivative and then you take it somewhere else, maybe physics or engineering, and that will help you to understand velocities. Okay, it's hard to tell which way it goes. Initially, I tried to refer to derivative or velocity in the sense when there is no limit to begin with, and then you don't have to refer to the velocity in this kind of complicated way, which is the direction and the speed changes continuously, and so that is somewhat complicated. But think about that if you're moving like this, that's your motion, that's your y equal f of x, then the velocity changes abruptly, and then there is you don't even have to say it is the derivative. We are talking about slopes. Okay, so slopes taken together is the derivative. Okay, so and that covers so much ground, just functions like this. They cover so much ground, so you can do all kinds of modeling, as I have shown you, with nothing but incremental change of the position. So we jump from one position to the next like this. So this is still time, and it means that we don't have to worry about what? We don't have to worry about the limit, because the slope of each of those segments is constant. So all you have to do in order to find what the derivative is, look as always, rise over the run, right? So that's the derivative. It is just changes from segment to segment, but does not change continuously, but incrementally, and that's why the limit is not an issue anymore. The only problem is, first, it's probably an approximation, and secondly, the derivative changes then abruptly. If I try to plot the graph of the derivative, y equal f prime of x, I'm going to end up with something like this. Something like this. Okay, so derivative is constant on those intervals, and then it becomes, and you jumps up and down. So if you're talking about some physics application, then it's probably not a convincing model if you think about it, right? So abrupt changes of velocity. You probably, I mean, if there are some kind of forces, gravity or whatever, spring, the velocity, not only the location but also the velocity, will be changing continuously rather than abruptly. But it's a good approximation, and it covers a lot of ground. You can run all kinds of simulations with it. So far, I've been trying to find something that I cannot model, and so far everything works out fine in that manner. Okay, so tangents, the idea of derivative as a tangent. So apart from motion physics, we're talking about the slope of the tangent line. The tangent line is the limit of what? So once again, this is the slope of the tangent line at x equals 0, x equal a, y equal f of a. Okay, so a, f of a, and then you have your tangent line. And so, well, this is also important to remember what this is. What is this fraction? It is rate of change over, if you want to be careful, you'd say it is the average rate of change. And then you point out over what interval it is the average rate of change. It is, so average rate of change, rather than instantaneous rate of change, which is what derivative is, of f over interval, which is a plus h. Okay, so in other words, this is a plus h, and we're looking at this incremental change, and we're looking at the slope of a straight line, and that straight line is very easily built in this fashion through these two known points, and it is also something that you need to remember is the name of this line. If this is tangent, then the other one is secant, yeah. Secant, once again, tangent touches, secant cuts. So these are the meaning of the words. Okay, so there's only one tangent per point, but there are secant lines for any 2 points. You can draw a line through those. So the secant line is not a tangent line because, well, you need 2 points, and that's the problem about tangent lines. How do you build it when there's only 1 point in common with the graph? How do you build it? You build secant lines and find their limit. Okay, so that's an important concept, obviously. So instantaneous rate of change, or instantaneous rate of change is what the derivative is. So remember that problem of how to estimate the derivative from nothing but the picture. How do we do it?
Add a bunch of secant lines.
Well, the thing is, you need a bunch of secant lines only when you're planning to have infinitely many of them and then take the limit of them. If you all you need is a one approximation, which nobody even requires you to do any particular quality, you don't even have to estimate how good it is, then you pick any secant line. Any secant line will do, the closer these 2 points to each other, the better the approximation is. So either you do that, or if it is even simpler, is well. So that let me show you. So that would be your secant line. You pick 2 points. So suppose this is A. I pick 2 points and draw a line through them. Okay, that does it. But if you can separate these 2 points, then you probably know that you can do better than that, because picking a point in the middle halfway will give you a better approximation. So a better way to do it, I think, is remember moving a straight edge along in such a way that the graph will touch the straight line given by the edge will touch the graph. Okay, so I think I did it before, so let me do it again. So if this is my point, AF of A, and I wanna create a tangent line. One was to zoom in. Remember, we did that. Another one is to do a line. So let me try to do it. Okay, that's not. That's not it. I'm trying to. It's supposed to be kind of a movable thing. Okay, like this. See, you're moving and you make sure that it passes through your point, and at the same time it is pretty much has only one point in common with the graph. Okay, so this roughly works out more or less. But if you're not sure, then move it around like this. Okay, so making sure that your slope is correct and and it passes through that point. So like this. So this is reasonable, even though it seems a little bit tilted to the left, or tilted to the left. Yeah, but it's pretty close to the truth. So this is the point. And that's how you do it. Another one we did was literally if you have an image. Well, if you do it at home, obviously, you have to take that picture, put it in paint, zoom in, or even better, you remember you blow up. You cut a little piece of the graph and you blow up and put it in some kind of grid, and that will give you the slope. Okay, so either way. Okay, so derivative is a limit. So you could do this picture on left can be done with a spreadsheet. So you can just have a bunch of secant lines, and so it will compute the tangent line for you easily. Now, just like continuity is a big deal, differentiability is a big deal too. So continuity, it is we just discussed that yesterday. Differentiability, it means simply that there is the derivative at that particular point. So function might be continuous but not differentiable, but not vice versa. So there are more continuous functions than differentiable. Example should jump at your head. A function that is continuous but not differentiable. What is it? Continuous, not differentiable.
Does that mean it doesn't have a derivative?
That's right, but the thing is, we're talking about one point at a time. So it might have everywhere it has derivatives, but if there's only one point where it doesn't.
Trig functions.
No, trig functions are fine unless you take the tangent, then the function is undefined at, say, pilot. What? The absolute value, yes. The absolute value is it. So as you can see, there is no break. Well, to the left, to the right of 0, there is nothing happening to worry about from any point of view. So we'll look at 0, and what's so special about 0? Well, there is no discontinuity, there is no gap, there is no break in the graph, but there is no tangent line. So if you just try to do what I just tried to do a minute ago with that straight line, what did like this? Which way? I could go, well, I mean, look at it. Come on, move it. Okay. It touches the graph, definitely. So you can, from that point of view, if you understand literally, the tangent line is a graph that touches straight line that touches the graph, then this would be it. But then you can have a bunch of those like this, and so on. So there are infinitely many of them, and so when there are infinitely many of them, well, it means that there is no derivative. If in any doubt, you can just go straight to the definition, and it will produce the exact same outcome. The limit does not exist. Ultimately, that's what it's about. So if you think graphically or geometrically, it is the tangent line zooming in on the graph. It should turn into a straight line. If it is a V-shaped graph, you zooming in, it's still V-shaped. The corner does not disappear no matter how much you zooming in it. It is the thing about mathematics. So you know, if you take that corner over there, well, it will be smoothed out eventually. But in mathematics, everything is you know, how do you say it? The absolute, yes. So if it is, hey, there's a corner there, then it remains a corner no matter how much you zoom in, and that is non-differentiability. That sign of non-differentiability. And you can certainly, that point is important, is that if you compare this poor behavior of the absolute value function and poor behavior of this function, you can see that how one is worse than the other. This second one is way worse than the first one. So the first one is continuous, not differential. This one is not continuous. So you can imagine what happens to those secant lines. They converge to a vertical line, and that's non-differentiability. Okay, so differentiability is a complex concept, and it only gets worse as you get to functions of many variables. But so some kind of general understanding is required, and one way is this. Another way is what we talked about a bit, and that's linear approximations. So you zoom in and it turns into a straight line. That's geometric understanding of certain algebra. Remember, you replace a function with a certain linear function. Okay, what does it mean geometrically? That's what it means. It means that you zoom in and the two graphs become indistinguishable. I almost did it over there. So if you imagine that little circle is blown up, then the red and the blue will not be distinguishable. So that's differentiability. That's linearization. Okay, so but that is the drawback of this analysis, is that it does it one point at a time. So that is just cannot work. So you have to ultimately think of derivative. And so by the end of the semester, you certainly should think about derivatives as functions. There's a function, you derive from it a new function. Not only algebraically, it doesn't matter how it happens, it's just there. So you don't know which one. It is, in a way, you can't be really sure which one derived from which. Is it say, if you know location, you can derive your velocity, or if you know velocity, you can derive location. So the word is a little bit funny here, but these functions kind of coexist. If you're driving, on the one hand, the location is there, but on the other hand, the velocity is also there. So which one is the first, which one is the second? It doesn't really matter. They coexist, pretty much. So if there's no problem with differentiability, these are just two functions that exist at the same time. You just derive the second from the first, because that's how algebra works. But they could coexist, and that's why the important skill is to be able to plot. Also, another typical problem for final is to plot the derivative from the function, and vice versa. Okay, so and that's where the increasing decreasing classification comes into play. So positive derivative, increasing function, negative derivative, decreasing function, and zero derivative, maybe vertical, maybe horizontal asymptote. So if in any doubt, so the derivative concept is kind of complex. But in any doubt, when you're plotting something, then it doesn't have to be that complicated. Just look at that picture again. Maybe behind it is just a kind of broken line, the green one, not the red one, the green one. So if you're looking at the graph and you're supposed to figure out what the derivative looks like, I don't know. You're looking at this graph and you're supposed to figure out what the derivative looks like. Okay. So what do? You imagine that In fact, it's made of dots connected by edges, okay? And then, well, there you go. And then it should be no trouble for you to figure out what the derivative is. So you can literally, it is not very profound way of doing it, but it's good enough. So put a few points close enough to each other so that the pieces of the curve between them is almost a straight line. Okay, and then just look at each of them separately and find out what the slope is. So I don't know, slope is equal to 2, and this is slope is 1. Okay, and over here slope is negative 1. Okay, this is once again slope 1, and so on, and then combination of these numbers will give you the derivative. Okay? Look puzzled? No? Okay, so like I said, it doesn't have to be that complicated. So you remember that behind every absolute definition there is some kind of approximation. At least in calculus, that's often the case. So behind the tangent line is a bunch of secant lines. Behind the derivative is a bunch of straight lines. The straight lines with their slopes. Okay, so some of the problems in fact, some of the problems that I was going to just talk for a minute about is the problems from descriptive, kind of non-mathematical, but you either have a picture rather than figuring out the slope. So you can still have that picture, the green picture on the right, given to you, and then they tell you not that it's a function. They tell you something else. They tell you that this function represents location as a function of time. Okay, and then describe what's happening. Kind of a different problem, but you solve it almost in the same way. So can you look at that graph on the right, and once again, suppose this is function represents location. That's the y-axis. The x-axis is time. And so what does it tell the story? Can you tell the story? Let me make a bigger picture.
Do you want to plot the derivatives?
Well, it's up to you. So you tell me. So if you want to, okay, that's the whole thing. Y location, x time. So what's the story? So the story then would have to be in words. So can you tell the story? What has happened?
The rate of change goes from...
Well, the rate of change when you're moving is what's the term?
Going at a constant speed
Okay.
until about...
Well, either speed or velocity is what you will be talking about. Okay, so I know I wouldn't be talking about concavity. You have to describe in pretty much layman terms, non-calculus terms in a way, what has happened. Okay, so point by point, 1, 2. So what? This is the beginning. So what is that? What do we have?
It starts at x
At 1 o'clock, we were 2 miles away from some origin of the universe. Doesn't matter. Okay, and then what happened after? What started to happen? The time started to progress. Okay, so let's progress in time. What's happening to us?
moving at 1 mile an hour.
It does appear that we're moving 1 hour roughly per hour like this. Okay, in the direction, that positive direction. Say maybe, well, you can, if you want to be specific, say this is north. So we start moving north, 1 mile per hour roughly, and then well, you see, so it's roughly, and then what's happening?
It slows down at
It
x.
slows down a little bit during the next hour. It's kind of slowing down to maybe less than that. Wait a minute. How should I be specific here? So if you're slowing down you're covering less. Okay, so like this, like this. Okay, so after at 3 o'clock, you have not reached the 4-mile mark. So you're moving slower than 1 mile an hour. Then you slow down even more, and then what? During between 3 and around 3:30, what has happened? You turn around, start moving backwards, and then the slope is the velocity is kind of slow, speed is slow, also maybe half a mile an hour, and then you don't speed up. In fact, you slow down even more, stop, turn around again, and start to speed up to appears to be speeding up over here. So that would be description. Okay, and vice versa. You imagine the story that we just told, and you have to produce the picture. Okay. Okay, so so there are a bunch of examples here, but I want to move one quicker. Notation. Remember, notation will be freely used for the derivative. There are 2, 3 different ways to use notation for the derivative, so they will appear freely and are almost at random. Okay, so the simplest motion of a ball thrown in the air, also part of it. So thrown in the air, so say y double prime is equal to negative g. That's the starting point. The acceleration is negative is g in the negative direction down. Okay, and then you this is pretty much Newton's laws almost all together here in one place. So remember what happens. How do we proceed from this? Yeah, pretty much integral. Yes, we integrate. So if you know the derivative, we know the derivative of what? This is y prime prime, right? So then you're moving downwards. You actually, this is the setup. This is the physical setup of what's going on. But if you want to discover what actually has happened to that particular ball thrown in the air, then you have to find, to begin with velocity. In the current velocity, find the location. So then we know the derivative of y prime, and how do we find y prime? We integrate dx. So integral negative g dx. Fortunately, it is a constant function, so there is no trouble. It will be negative g x plus c. And then you do it one more time, and c is the initial location, and so on. So that is a derivation of formulas that might be, you probably saw a long time ago as a given. So a quadratic equation that represents your motion, but this is how it actually happens with anti-differentiation, and that's how Newton did it.
Now, since it's meters, 9.8 meters per second squared.
Yeah.
What's the squared do? Does that just mean like
Per second per second.
What's that?
The velocity is meters per second. Then how does the velocity change if not per second?
Second squared.
And that's what second squared is, per second per second. So it's a meter per second squared is meter per second, right? So it's like taking that difference quotient twice. Remember, the difference quotient, the function is measured in meters, okay, and that's the numerator, f of a plus h minus f of a. So these are meters, but then you divide by h, which is time, and measured in seconds. That gives you the velocity, but then you do it one more time for the acceleration. So you do some stuff with this. Well, let's write that out. Well, I don't want to write it out actually, but you can imagine if you carry out this procedure one more time to this expression, and then you will have meters per second divided by h one more time, and that gives you per second squared. It is weird to put it this way. It's just the more compact way. I think in the old times that's exactly the way they would say it. Meters per second per second. Yeah. So and the result is a parabola. If as we talked about a bit, if there is an additional horizontal motion as well, then there is no force as far as the horizontal motion is concerned, which means that it will be a linear motion in the y double prime equal to 0. Oh, I'm sorry, x. Well, x double prime is equal to 0. This is supposed to be with respect to time, otherwise it is just too complicated. So x double prime is equal to 0. Here, x and y are both dependent variable, and the independent variable is t, which is just a more advanced way of doing it. Once you have more variables involved, then x, you don't use always x as the as one of the one of the independent variables. So in this particular case, x and y are dependent, both dependent on t. Okay, and so in this particular case, x depends on t. The second derivative of x with respect to t is 0. So what does it tell you about x prime?
It's a constant.
It's a constant, so you're moving with a constant speed horizontally, and that's why you have a problem. That's why you have a problem. The result is a parabolic motion. Okay, so some problems are certainly that we have considered were kind of bulky. So any kind of motion, even this problem is kind of bulky, and so you don't have to really give it a lot of thought to bulky problems as far as the final is concerned. It is the problems will be small in size, evenly distributed. So I'm not sure about differentiation, what techniques of differentiation, what needs to be discussed, other than, well, the derivative of the product is not the product of the derivatives, but when it is composition, it is. So don't jump to conclusions. And once again, rounding again and again, in my experience, the compositions always come up, and they're always troublesome. And so the chain rule. So let's do one more example of the chain rule. So just yeah.
In that previous example, if x prime is a constant, wouldn't x be linear?
Yes. So x is linear. So x is linear, y is quadratic. So this is the I didn't make the next step. Y is quadratic. So you're moving then vertically. There's like two separate motions. One with respect to x, one with respect to y. And it's like either you're standing, you are throwing a ball, like if you are throwing a ball forward, but you're standing behind it. You don't see forward progress, right? If you don't see the perspective, then it's moving. Just you will see it going up, and then you're going down. Okay, so that's the vertical, but that's your y. Okay, and it is quadratic. So going up, slowing down, stopping, and then starting to speed up and going down. That's what you see if you're standing behind it. If you are either that cannoner or you were just throwing the ball. On the other hand, if you're lying on the ground in front of that of whoever is throwing the ball, you don't see the rise of the ball. So you see what I'm saying? So the ball is thrown this way. So one person is actually thrown, and it stands here, and it does not see the rise. Or it doesn't see the depth, but the other person lying down like this. Okay, he doesn't see what does he see?
He doesn't see the rise.
He doesn't see the rise. So one sees the depth, one sees the rise, and so this one is responsible for y, and that is responsible for x, and they have two different observations, and then they could meet together, write down what they saw, then meet together, and they will figure out what actual motion was. They have enough information to plot the graph. Okay, and then they will discover that it's a problem. Okay, I guess I'll pay next time the more attention about the composition and chain rule. Always a good idea to review it. And so, but we start with on Monday. Okay.